You're listening to Wurth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Electronic technical specialists who will shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast. In the age of going green, energy efficiency is everything. Energy efficient devices are important components for saving resources and also protecting the environment. The more efficient the electronics, then the longer the battery service life for mobile devices. And then in large-scale industrial and server installations with thousands of loads, the energy requirement is extremely reduced. The basis for energy-efficient devices is essentially influenced by the power supply unit. While the linear regulators that were widely used in the past were voltage regulators, mainly switch-mode power supplies are found in modern power electronics. The continuous reduction in processor voltages has played its part in this. A few years ago, switching frequencies up to 300 kilohertz were widespread, whereas modern switching controllers usually clock with frequencies of around 800 kilohertz or more. The switching losses, but also the power inductor losses, are important aspects in the design of switching power supply units. New iron alloy group material composites have further reduced core material losses for high current power inductors. Wurth Electronics MAPI, M-A-P-I, is a component series whose unmatched material selection and manufacturing technology combines the optimal use of inductance and current carrying capacity with low internal losses. Red Expert is our free platform, and it helps the developer determine the most accurate data for DC and AC current losses in power inductors in the application environment. Core loss calculations based on Steinmetz equations quickly reach their limits here. MAPI is one of the latest and most innovative series of coils from Wurth Electronic. Conventional coils mostly used enameled copper wire wound around the core and soldered or welded to the terminal with a clip. The outer shielding ring is then mounted and bonded with the inner core and the winding. The MAPI, however, breaks new ground, and the winding is contacted directly with the component's connection pad without the soldering or the welding. Saving the clip allows the effective diameter to be increased, so this means that fewer windings are needed for the same inductance values. This results in a considerably reduced DC resistance of the winding. In the application, the start of the winding of the coil is usually connected with the switching node of the switching controller, and you can usually find a marking on the component that indicates this. So this means the spatial expansion of the hot switching node is minimized, and the coupling effects through the outer part of the winding at a stable potential are also shielded. The core consists of an innovative metal alloy. It's pressed around the winding. This presents the MAPI series high inductance values with a small package size. At the same time, the special construction of the core has a self-shielding effect. The core material itself is temperature stable with only a slight drift and soft saturation behavior. A protective layer is also applied around the core, rendering the surface resistant against environmental influences. The MAPI series components are available in many different package sizes, from 1.6 square by 1.0 millimeters up to 4.0 square by 2.0 millimeters. But what about the losses in the power inductors? The losses of a power inductor arise from core material losses and winding losses. The winding losses themselves can be divided into DC current losses, essentially influenced by the DC resistance of the winding, and the AC losses of the winding that arise from skin and proximity effects. You can use several methods to determine the AC losses of the winding, such as the dowel. Ferreira or Nan-Sullivan methods. The importance of AC losses in modern switching controllers could actually be determined with a simple setup and measurement of the relevant losses. As an example, we take a buck converter with an input voltage of 24 volts. At the output, there is 12 volts with 2 amps. The clock frequency is 500 kilohertz, and in our first attachment, figure 1, a Wee Mappy 4020 series power inductor with 2.2 microhenry is compared with power inductors of the same package size. It is clearly apparent that with all the coils measured, the AC losses outweigh the DC losses. The coil is one of the most important components in switching controllers, so this means the accurate determination of the losses and heating is a critical step in the selection of the right component. In order to be in a position to predict heating, the AC losses first have to be accurately determined. Historically, core losses were determined with the Steinmetz model, then later with the modified Steinmetz model or the generalized Steinmetz model. In our attached figure 2 of this podcast, you can see the 3 models and their differences. The original Steinmetz model showed P sub V as the core losses per unit volume. F was the switching frequency, and B sub PK was the magnetic Ferreira modulation. F sub EQ is the equivalent frequency, and that results in non-sinusoidal modulation for a deviating duty cycle. And then finally, K, alpha, and beta are the constants of the core material determined by extensive measurements with a ring core. Again, the attached figure 2 of this podcast will show these models and the equations in detail. The main drawback of the Steinmetz equation is that it mainly applies for sinusoidal excitations, and determination of the coefficients is usually only measured with small signals. However, in most applications in power electronics, the coil current is not sinusoidal, and the currents are large signals of several milliamp up to several hundred amperes. There are also other models that attempt to resolve the problem of non-sinusoidal waveforms by separating hysteresis and eddy current losses. Here, the empirical Steinmetz equation has proven to be a useful variant, but it only offers high accuracy for sinusoidal currents. However, the various Steinmetz models only work optimally with a duty cycle of 50% and within a restricted frequency range. In addition, on account of the high complexity in finding the magnetic path length, the determination of the core losses with the help of existing models for iron powder and metal alloys is not only demanding, but the accuracy is also subject to some serious fluctuations. And for inductors that consist of several different core materials, estimation of the losses is only possible with great effort, if at all. But now there is a new model. Wurth Electronic has developed a highly modern model. It's capable of accurately determining the complete AC losses in inductors. This model is based on empirical data obtained with a real-time application setup. Here, the total losses of the inductor are divided into AC and DC losses. Empirical data are measured with a DC to DC converter. A pulsed voltage is applied to the inductor, whereby the input power and the output power are measured. Input power minus the output power equals the loss is determined on this basis, and the AC losses of the coil are separated. This procedure is used to measure the different parameter settings, such as fluctuations in the magnetic modulation, switching frequency, ripple current, etc., and this empirical data is then recorded. With the help of this empirical data, our model is created for calculation of the AC loss. Advantages of the Wurth electronic AC loss model include the accurate determination of losses for every given duty cycle. The empirical data is based on a DC to DC converter, it's accurate across a wide frequency range, and it also considers the smallest changes in the core material and the winding structure. Other benefits are that it's accurate for determining the losses in components with iron powder and metal alloys. It's capable for every possible core design and winding structure, and also includes AC winding losses. Wurth Electronics' Red Expert model has been extensively validated and also compared with existing models and measured data. AC losses for different materials, such as the WE Superflux, iron powder, nickel zinc, and more have been measured over wide duty cycle and frequency ranges, and then compared with theoretical models. You can see this example in Figure 3 attached in this podcast. The graphs in Figure 3 show the core losses determined with the Steinmetz Power Equation, or PST, the modified Steinmetz Equation, PMSE, and the generalized Steinmetz Equation, PGSE. Red Expert shows the AC loss following calculation with the AC loss model from Wurth Electronic. The measured AC loss is real. Red Expert is the free online design tool from Wurth Electronic used to select a suitable power inductor for the respective application. Red Expert is an easy-to-operate and effective tool, enabling components to be compared and selected within the shortest time. The user first enters the input and the output parameters for the required topology, and then Red Expert calculates the necessary inductance values and displays the suitable inductances. The calculation of AC losses in a magnetic component is just as critical as it is complex, but not with Red Expert, since the AC loss model is already integrated. Based on accurate calculation of the complete AC losses, the application is also suitable for temperature estimation. The losses are displayed graphically over the complete input voltage range in order to also take extreme scenarios into consideration. This way, the most energy-efficient power inductor for the respective application can be selected in no time. In order to determine the right inductor for a buck converter, just enter the existing input voltage range and the output voltage range and the current in the input screen, as well as the switching frequency, the diode flow voltage, and the targeted ripple current of the inductor. Then you will get the suitable power inductor along with its anticipated ripple currents and the losses in the application. There's also a manual loss calculator, and this calculates the losses for power inductors independent of the topology. Only the frequency, the duty cycle, and the ripple current or the voltage drop have to be entered, and Red Expert takes care of the rest. Since Red Expert is a web-based tool, nothing has to be downloaded or manually updated. In summary, WeMappy power inductors offer maximum power in the smallest of spaces. With the innovative core material and the sophisticated design, new standards have been set. For energy-efficient switching controllers, the WeMappy is best selected with Red Expert. This integrates the world's most accurate AC loss model, which renders the parameters of frequency, ripple current, and duty cycle with high accuracy over a wide range of values. Attached images are available in most podcast streaming networks. To view all images, visit www.we-online.com/podcast. To download the complete application note discussed today, visit Wurth Electronic online at www.we-online.com/appnotes. You're listening to Wurth Electronics' What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Electronic technical specialists who will shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics' What's Up podcast.